Okay, we talked about first order integrated rate law in the last video, and so now we'll talk about second order integrated rate law. So reminder that we know two things about the rate. We know that the rate is equal to the rate law, which is what you see over here on the right, and it is also equal to the change in concentration of a reactant divided by the change in time. Now this could also be true of a product, but we're wanting to relate it to the rate law, and the rate law has the reactant in it. So that's the reason it is written in this way. And remember, this negative is here because reactant concentrations are decreasing, but we want our rates to be positive. So that negative and negative will cancel to make a positive. So this is for second order that we're discussing now. The way to find the rate in terms of a change in concentration is no different, but now we have a 2 as our power on our concentration in the rate law because we are talking about second order. So we're going to integrate this. So here comes the calculus fairy. She takes this, she integrates it, and we get this second order integrated rate law. Now again, this equation is given on your equation sheet. You do not have to memorize it, but you have to be able to recognize that this is the equation that we can use only if we have find the concentration at a specific time, or it may allow us to find the concentration at the beginning. If we know both of those, it could allow us to find K, and if we know both of those in K, it could allow us to find T. So we could solve for any of these variables as long as we know the others. The variables are the exact same as they were in the first order integrated rate law. We have our concentration at some time, our concentration at the beginning, our rate constant, and our time. And then the only thing that's different is instead of natural log, we have the inverse of these values. And also there's no negative sign in front of our K. So you'll notice here that our slope, if we're thinking about this in terms of y equals mx plus b, our slope is going to be positive. So let's go ahead and rearrange that into y equals mx plus b form. So we'll move this part over there. So now we have our y as our inverse of our concentration. So 1 over the concentration, or concentration to the negative 1 power. It's the same thing, right? Concentration at time t to the negative 1 is the same thing as 1 divided by. And then we have kt, and again notice that this is a positive slope. And then 1 over our concentration at the beginning will be our y-intercept. So if it is second order, then this equation is true, and only if it is second order is this equation true. Therefore, y, 1 over the concentration, versus x, time, should give us a straight line if it is a second order reaction. So this is a way we can determine if something is second order, because this plot, 1 over the concentration versus time, will only give me a straight line in a second order reaction. So if we look at this plot, we have 1 over the concentration, or the inverse of the concentration, plotted along the y, and time along the x, and boom, is a straight line. I can say for sure this is a second order reaction. On this plot, this y-intercept is equal to 1 divided by the concentration at the beginning, and my slope is positive, and it is equal to K, my rate constant. All right, so let's look at an example problem here. We have a 1 reactant reaction, and there's a coefficient of 2, but remember that has nothing to do with the order necessarily. And then that forms or decomposes to form 3 products. We have the data of time and concentration. So remember when we do the table method, like we did in the first lesson, that's when we're going to have multiple experiments. When we're doing integrated rate law, we're going to have one experiment where we follow that experiment over time. So here we're following this reactant over time, and we plot that data in 2 different ways. So we tried it as the inverse, and we also tried it as the natural log. Now, which of these gave us the most straight line? The inverse plot gives us a more straight line. So that tells us that it is what order? Well, the natural log plot is for first order, right? And that didn't produce a straight line, so I know it's not first order. But the inverse plot did give me a straight line, so that means this must be a second order reaction. So, to write the rate law will be simple. Rate equals my reactant, rate equals K, my reactant concentration raised to its order. And from the plot, I know that because the inverse plot gave me a straight line, it's second order, and this is the only reactant, so it goes there in my rate law. Don't forget to include K when you write the rate law. And also, in this case, my coefficient is my order, but that doesn't mean that coefficients are ordered. Okay? It just happens to be a coincidence in this case, so watch out for that. You have to have experimental data to figure out the order. You can't just use the coefficient. All right, now we want to find K. If we had numbers on this plot, it would be easy to find K because K is the slope of this line, right? But they didn't give us any numbers on this plot. So we're going to have to use this data over here to find K. Remember from our previous example that to find K, we're going to use our concentration at time 0 in our integrated rate law, and then we'll just pick some other time and use that concentration as well. So we have our rate law equation, our integrated rate law equation, and they just kind of flipped it over because they're trying to find K. All right, and then they just kind of plug in. So here is our concentration. They picked their time of 100 seconds. And so they plug in the concentration at that time right there. And then here's the concentration at the beginning, right here. And then we do 1 divided by that minus 1 divided by that. And then whatever that equals, we're going to divide by 100. And so we come up with this value for our rate constant. Now recall that our order is 2. And if we look at the units, we've got 1 divided by molarity divided by seconds. So molarity is on the bottom and seconds is on the bottom. So 1 over molarity times seconds, or molarity to the -1, second to the -1. This is the unit if it is second order. So you can memorize that, or you can look at the units within the problem. Here we have 1 over molarity minus 1 over molarity. When you subtract, your units stay the same, and then we divide by seconds, so seconds is also under the fraction or raised to the -1. Okay, in the next example, they're looking at data from an experiment which examines a change in concentration for a second order process. And it was used to plot the graph below. So this is obvious, right? Inverse versus time gives me a straight line, so second order. The task here, though, is to sketch a line that would be expected if we repeat this at a higher temperature. So at a higher temperature, do you think the reaction is going to go faster or slower? Well, at a higher temperature, I would suspect that it would go faster, right? Well, that's not going to change where it starts. But if it goes faster, we're going to have a higher value for K. So I'm guessing that it would climb faster. What if it was a lower temperature? Still going to go up. Still going to have a positive slope. Forgive this section right here. But just go up slower. What if they said a catalyst was used? What would that do? Make it go faster, right? So the slope would be more positive. All right, let's see how they sketch that. Probably better sketch than me. So it's going to go up faster. Same initial, but going up faster because AB is going to decrease more rapidly. So if this number on the bottom is getting smaller, the inverse is actually getting larger, and it's going to do so more quickly at a higher temperature. All right, so you've seen first order integrated rate law. This is now second order integrated rate law, and that's all for this lesson.